Today, we will present our mid-project report titled Design and Development of a Low-Cost PEM Fuel Cell System Using SolidWorks and matlab. Our project combines mechanical design, simulation, and mathematical modeling to develop an efficient hydrogen fuel cell system. During this presentation, we will explain our design process, simulation results, current progress, and future work. This is the outline of today's presentation. First, I will introduce PEM fuel cells and explain why they are important. Then, as you can see, we will discuss our project objectives. After that, we will present our SolidWorks design and explain the 8 main subsystems. Next, we will show the MATLAB model and the Simulink dynamic simulations. Then, we will present the SolidWorks simulations, including thermal and structural analysis. Finally, we will summarize our progress and discuss the remaining work. First, let's understand what a PEM fuel cell is. As you can see in the slides, a PEM fuel cell converts hydrogen and oxygen into electricity through an electrochemical reaction. Compared with conventional energy sources, PEM fuel cells have many advantages. They produce zero harmful emissions because the only byproduct is water. They also have high efficiency, operate at relatively low temperatures between 60 and 80 degrees Celsius, and can start quickly. The chemical reactions are shown on the slide. At the anode, hydrogen is split into protons and electrons. The electrons travel through an external circuit to produce electricity while the protons move through the membrane. At the cathode, oxygen combines with the protons and electrons to produce water. Our project includes 4 main parts: designing the complete fuel cell in SolidWorks, performing engineering simulations, developing a MATLAB performance model, and building a dynamic Simulink model. This was Asiya. I will leave you with my member called Kata.
This slide shows the overall system designed in SolidWorks. That complete full cell consists of 8 major subsystems, each responsible for a specific function. These include the full cell attack, hydrogen supply, air supply, the cooling system, power management, structural enclosure, sensors, and the control and safety system. Together, this component allows the fuel cell to operate safely and efficiently. And here we can see the integrated CAD model, the thermal simulation. The thermal simulation helps us understand how heat is distributed inside the fuel cell during operation. The results show that the temperature remains relatively uniform, which is important because excessive heat can reduce efficiency and damage the membrane. These thermal results are also used as boundary conditions in our MATLAB model. This slide explains the 8 subsystems in more detail. The full cell attack contains 24 cells connected in series, and it's the main source of electrical power. And the hydrogen inlet system controls the hydrogen flow and pressure. And the air supply system provides oxygen to the cathode using a blower. And the coolant system removes excessive heat and keeps the operating temperature between 60 and 80 degrees Celsius. And then the power management system converts output voltage to the required level and improve efficiency. And the structural enclosure supports and protects all the components. And finally, the control and the safety system manage startup, the shutdown, and the emergency protection. And together, these 8 subsystems ensure the operation. Now I will leave you with my teammate, Doha.
To predict the performance of the fuel cell, we developed a MATLAB model using the infinite semi-empirical equations. The model calculates several voltage losses, activation losses, ohmic losses, and concentration. These losses reduce the actual voltage produced by each cell. Using these equations, MATLAB calculates the cell voltage, stack voltage, output power, hydrogen consumption, and overall efficiency. This allows us to predict the fuel system performance under different operating conditions before building a physical prototype. This slide shows the simulation result obtained from MATLAB. The polarized curve shows that the voltage decreases as the current increases because of different voltage losses. The power curve shows that the maximum power is approximately 1.6 kilowatts at around 130 amperes. The efficiency starts above 70% at low loads and gradually decreases to around 41% at maximum load. Finally, the hydrogen consumption increases as the current increases, because more hydrogen is required to produce higher electrical power. Overall, these results agree with the expected behavior of PEM fuel cells. Now I will leave you with my teammate Mohammed.
So moving on to the slide number 9, MATLAB model parameters and key results. So this table summarizes the most important parameter used in our MATLAB model. So the stack contains 24 cells, each with an active area of 100 square centimeter. The operating temperature is 333 Kelvin or 60 degrees Celsius. The hydrogen pressure is 1.5 atmospheres. Using these parameters, our model predicts an open circuit voltage of about what? 30 volts, a peak power of 1.6 kilowatts, maximum efficiency above 70%, and hydrogen consumption of about 117 grams per hour at full load. These values shows that the model performs realistically. So moving on to the slide, talking about Simulink dynamic system model. Unlike MATLAB, which provides steady state calculations, Simulink allows us to study how the system behaves over time. Our model consists of 6 connection blocks: the control system, hydrogen supply, air supply, fuel cell stack, thermal management, and power management. The model includes PID controllers to regulate temperature and airflow. It also simulates startup, normal operation, and shutdown using state flow. These help us evaluate the dynamic performance of the complete fuel cell system. So, moving on to the Simulink step load results. In the simulation, the load changes from 50% to 100%. At 60 seconds, then returns to 50% at 120 seconds. When the load increases, the stack voltage decreases from approximately 20 volts to 12 volts. The temperature increases by about 3 degrees Celsius, but the PID controller quickly returns it to the desired operating temperature. The DC bus voltage remains stable throughout the test, showing that the control system performs well. These results demonstrate that the fuel cell responds smoothly to changing operating conditions. So, giving the floor to my teammate Zainab.
We also performed SolidWorks simulations. First, the thermal analysis shows that the temperature varies from 60 degrees Celsius at the edges to approximately 76 degrees Celsius at the center. This remains below the maximum safe operating temperature of the Nafion membrane. Next, the structural analysis evaluates the stresses caused by the clumping force applied to the bipolar plates. The maximum deformation occurs near the center, but it remains within acceptable limits. Overall, these simulations confirm that our design is mechanically and thermally reliable. Now, for this slide summarizes our project's progress. The literature review and the CAD assembly are fully completed. The MATLAB model is approximately 90% complete. The Simulink model is about 85% complete. The flow simulation and engineering drawings are still in progress. Overall, the project is progressing according to schedule. So to sum up, we successfully designed a complete PEM fuel cell system in SolidWorks. We developed a MATLAB model that predicts fuel cell performance, including voltage, power efficiency, and hydrogen consumption. We also built a Simulink model to analyze the dynamic behavior of the system and completed thermal and structural simulations. Our remaining work includes completing the flow simulation and a cost analysis. Thank you very much for your attention.